So the last topic we're going to cover today is the remainder of a Taylor polynomial. So if you think about the nth degree Taylor polynomial, that gets you close at a certain point, but there's still a little bit of variation or error if you were to compare it to the true value of the function. So you can think about the function as being the nth degree Taylor polynomial, p sub n of x, plus some sort of remainder or error value. So you can think of, if you were to solve this equation for r sub n of x, then this would just be equal to f of x minus pn of x. And we'll see that down below here highlighted as the error. So we just take the absolute value of that and we call it the error associated with the Taylor approximation. We also have a nice bound for our error where, given a Taylor approximation for a polynomial f of x and its remainder term, we know that it's going to be bound by some by the n plus 1th derivative evaluated at some point z over the rest of the stuff that we usually find. So the thing about z that you need to know is that you have an interval I that contains c, and the interval also contains x. So you can think about a number line. And as we saw earlier on, the Taylor approximation is only good around a certain point, right? So you have your polynomial, or you have your function f, and then you'll have a Taylor approximation that's like pretty close to it. Maybe this is, say, p n of x for some n. So you know that there's this interval where it's really, really good. And so you can think about this as I, your interval I. And there's a point that we center it on, right, that we call C, for which not only is the Taylor approximation very, very good, it's actually equal to it at that point. That's actually how we build the Taylor polynomials, from that point, and then we say it's good on the sides. So for any value x in this interval, let's say maybe x is right here, the remainder, r sub n of x, is equal to this expression here, the n plus 1th derivative of the function evaluated at z over n plus 1 factorial times x minus c to the n plus 1. So where is that z? What Taylor's theorem says is that z has to be here. Z has to be between x and c. So z lives here. But we don't know where exactly. So what we could say about z is that x, the point at which we're evaluating typically, is less than z, is less than the place at which we're centering. So this is your center, right? That's the thing where we build the whole polynomial off that. We evaluate the derivatives here at c. We take x minus c to the whatever power we need. And then x is the kind of location of interest, if you will. So let's just think about that for a quick moment. Let's go back up to the previous example, thinking about what x and c are. In this example, in example number 7, because we're Maclaurin, c was equal to 0, just by definition of what a Maclaurin polynomial is. What we used for x was 0.1, right? Because remember, this was our function here, f of x. So we saw that f of 0.1 was the natural log of 1.1, and therefore P4 of 0.1 was approximately the natural log of 1.1. So that 0.1 that we used in our Maclaurin polynomial of the fourth degree is x. If we look at this on a number line, here's c, here's x. So if we wanted to evaluate the remainder or error that was introduced in using the fourth degree Maclaurin polynomial, we could bound it, or we could say the error was equal to that, that expression we just saw, and we know that z is some value strictly between 0 and 0.1. So we're going to use that fact. We're going to try a different example, but we're going to use that idea in determining the accuracy of an approximation. So what I mean by that is that we're going to look at the third degree Maclaurin polynomial for sine of x, and we're going to say how accurate it is. So basically what's going to happen is this is what we really want to do. So we want to find two numbers that we know are going to be below and above sine of 0.1. So those are the two things that we're after. The way that we're going to do that is through a Maclaurin polynomial. So let's save ourselves the trouble of working out the third degree Maclaurin polynomial for sine of x. It's already given here. So then once we do that, we know that per Taylor's theorem, sine of x equals the third degree Maclaurin approximation plus some error term, the remainder term. So if I were to write this out, I would have x minus x cubed over 3 factorial. And I'm going to add to that the error term or the remainder term, because I know that the Maclaurin approximation is not exactly sine of x near 0, but it's pretty close. And also what Taylor's theorem says here, if we take this guy and use Taylor's theorem on it, we could say that R3 of x is equal to, let's look at what it says. We have to go up a derivative, so this is going to be the fourth derivative of z over n plus 1, so n being 3, we'd have 4 factorial times x to the fourth. So what we need to know is what's the fourth derivative and where does z live? So let's think about z really quickly. So we're Maclaurin, so we're centered here at 0. This is c. And we're going to use it to approximate sine of 0.1. So we have 0.1 here. So we have, let's see, this is x. So z lives here. So 0 is less than z is less than 0.1. The next thing we need is to know what is the fourth derivative of sine. So it goes cosine is the first derivative, then negative sine, then negative cosine, then back to sine. So the fourth derivative of sine is itself sine. So we can go ahead and say that this is sine of z over 4 factorial times x to the fourth. So we have an expression for our remainder term. And what we're going to do is we're going to have to be kind of clever about saying what the boundaries are for that remainder term. So we know that the maximum value for z is 0.1, and that's great. But we don't know sine of 0.1. That's actually what we're after. So let's just be more generous with our boundaries. So we can go ahead and say that -1 over 4 factorial times x to the 4th is less than sine of z less than sine of z over 4 factorial times x to the 4th, which is less than x to the 4th over 4 factorial. And that's because -1 is less than sine of z is less than 1 always. So now what we'll have is a lower bound for what our kind of like worst case on the left side is for the remainder, and then an upper bound for the remainder. So the minimum P3 is going to equal, the minimum approximation is going to be x minus x cubed over 3 factorial minus x to the 4th over 4 factorial. And then the maximum approximation is going to be x minus x cubed over 3 factorial plus x to the 4th over 4 factorial. And those two things came from here and here. So now that we have those, we can go ahead and plug in (0.1) for x, and we would get 0.99829, and we would get 0.0998375. So these are the two numbers that we were looking for. So what we can conclude is that 0.99829 is less than sine of 0.1, and that has to be bounded above by 0.099835.